So now I'd like to introduce Dr. Westall. Dr. Westall is a senior lecturer at Monash University Medical School, a consultant chest physician at the lung transplant unit, as well as physician in charge of the paediatric lung transplant program at the Alfred Hospital. His research honours include a Young Investigator Award from the Thoracic Society of Australia and New Zealand in 2006. And tonight he will be presenting From the Darkest Hour to the Gift of Life, a Journey in Transplantation.
Robin, thank you very much for that introduction, and can I also thank the organisers for the invitation to speak tonight, and also commend them on putting together Melbourne's contribution to the Day of Immunology. My remit is transplantation, and I introduce it with an image of a chimera, a mythical creature made up of many body parts. But of course, transplantation isn't a myth, and I'll be talking about the reality of solid organ transplantation. We're going to take a little bit of a journey through the history of transplantation and see how it does overlap with the history of immunology. So, what am I talking about? Well, transplantation is the process of transferring solid organs from one individual to another. And we are talking about heart transplantation, lung transplantation, liver transplantation, kidney transplantation, intestinal transplantation, pancreas transplantation. Usually in isolation, but occasionally in combination. And graft rejection is an example of where the immune system is doing what it's supposed to do, see something that's foreign and trying to remove it. But of course, this is detrimental to the transplant recipient. So transplantation isn't a new concept, and in fact, if you go back to the 17th century, you have the first description of a bone graft, where bone was taken from a dog's skull and was used to repair a defect in the human cranium. Move forward 200 years and you have the first description of a skin graft, albeit in the same individual, skin being taken from one area of the body and grafted onto another part of the body successfully. And over 100 years ago was the first description of a corneal transplant for somebody who had developed cataract following exposure to lime. But these are all examples of what we call tissue transplantation. What I'm going to be talking about tonight is solid organ transplantation. And the history of solid organ transplantation is a lot more recent. Indeed, the very first kidney transplant was done by Joseph Murray in 1954. And here is the picture of the kidney recipient next to the kidney donor. And you'll be struck by the remarkable similarity between the two of them. And I'll come back to that a little bit later. And Joseph Murray went on to be awarded the Nobel Prize for Medicine in 1990 in recognition of his pioneering surgical work. James Hardy, and this is in my area of interest, the very first lung transplant in 1963. And he went on to do the very first xenotransplant, which was a cardiac transplant, a heart transplant. And when I introduce the term xeno, we're talking a transplant where the organ is taken not from a human, but from a higher primate, and in this instance, from a baboon. And what he did was do a baboon transplant, taking the heart from a baboon and transplanting into an individual who was extremely sick with heart failure. It was unsuccessful and the patient died 2 hours later. It also had some very dubious ethics associated with it. This patient was so sick he was actually in a coma, and the pioneering surgery was discussed with the individual's family, and they were obviously impressed and keen to consider the very first transplant. And they presumed it was going to be a heart transplant. They were never actually told that it was a baboon heart that was actually going to be transplanted in. And I suspect we wouldn't get away with that today. In the years that followed, a number of pioneering surgeons did the very first transplants in livers, pancreas, and heart transplantation. And many of you may know the name of Christian Bernard, who did the very first heart transplant. And these guys were very much the celebrities of the day, and Christian Bernard ended up on the front page of Time magazine. As an aside, Christian Bernard was undoubtedly a charlatan and an opportunist. The leading workers in the field of heart transplantation were at Stanford University in the US, and a guy called Norman Shumway put together a 20-year program of experimental work with the view that at the end of which they would do the very first human heart transplant. And as with many leading institutes such as this one here, there are many junior fellows who come through to shadow and see how the experts do it. And Christian Bernard was indeed one of those. And he came as a junior fellow just to observed and saw what they did, and quickly rushed back to Cape Town in South Africa and took all the glory for doing the very first heart transplant. And of course, we no longer remember who did the second-hand heart transplant, which of course was Norman Shumway, who did all the pioneering work. But what was also forgotten in the realms of time is that they were spectacularly unsuccessful. What these pioneering surgeons were able to do was show from a practical, logistical, surgical point of view, you could take an organ out and you could reconnect it to the vascular supply, and you can give the appearance that it works well. And indeed they did work well for hours and days and weeks, but nothing longer than that. And the reason was that they were all universally rejected. And these pioneering surgeons hadn't kept a pace with the immunologists who were doing work in the area. So, change in tack. What is the immunology of transplantation? And I'm going to go through a number of the milestones. And the first one I'm going to focus on was the description in 1901 by Lansing of the ABO blood group system. And we can think of these as the first transplant antigens, if you like, or the first rule of transplantation. Many of you will be aware of this, but each one of us has a specified blood group, and our blood group is defined by the sugar molecules that are on the surface of our blood cells. If you're blood group A, you have a certain configuration of sugar molecules, blood group B different. For those of you who are A, B, you have both of them on the cell surface, and those who are blood group O, you have none of them on the surface. And what that also means is that depending on what blood group, you may have antibodies in your body against the other blood groups. So I know that I'm blood group A, and I know that in my circulating around, are antibodies against the B sugars. What that means is that if I was to inadvertently receive a blood transfusion, receiving blood which was blood group B, not my own type, my body, my immune system, my antibodies would destroy it. And the same is true for transplantation. So one of the first rules of transplantation is that if you're going to have a donor, it must be the same blood group as you. Blood group A into A, B into B, and so on. The next key development in transplantation is work done by Sir Peter Medawar and colleagues during World War II. And Sir Peter Medawar is very much the father figure of transplantation. And he was doing work during World War II, and in particular during the Battle of Britain. And the Battle of Britain was an aerial fight between the RAF and the Luftwaffe. And it went on for a number of years, in 1940 and 1941 in particular. And it was Winston Churchill who came up with the term the darkest hour, and he was relating to the large number of deaths that were occurring, particularly in London and the southern states, or the southern counties of the UK, during this period of World War II. And there were many deaths, and people weren't dying immediately from the bombs. Many of them were dying days, weeks, a month later because of complications of burns. And people realised that if you could do skin grafts, these were life-saving, but there wasn't enough skin around. And what they wanted to set up was a repository of skin, if you like, a skin bank, and then use this to save these people who were dealing with burns. But they realised that if you did a skin graft between two different people, they were invariably rejected. So the Ministry of War, not the Ministry of Health, recruited Sir Peter Medawar to basically define what is occurring with rejection. And this is in essence what Peter Medawar did. He basically was working in a mouse model, and he took mice which were genetically identical and did a skin graft, taking skin from one and grafting onto a mouse with the same genetic background, and he showed that if the genetics are the same, the graft was accepted and tolerated, and the graft survived. In human terms, you can think about doing a skin graft between identical twins. And indeed, if we go back to that very first renal transplant, that was indeed done between identical twins that had the same genetic background, and this is why the graft was accepted, because it was not seen as foreign. But of course, in an ideal world, we'd all have an identical twin who would be on hand to provide us with organs if we ever develop end-organ disease. A nice idea, and in fact this is the basis of the film Never Let Me Go, that came out last year. The premise was that we all have a clone whose existence is purely to provide us with an organ when we develop end-organ disease. I quite like the idea of there being curing like this, but that's merely an aside. What he went on to do was, what happened happens when you do a skin graft between two individuals who don't have the same genetic background. And what he was able to show is that they weren't accepted, and in fact, in a fairly predictable manner, these skin grafts were seen as foreign and were rejected. And again, in human terms, or cartoon terms, you can think about the skin graft between two individuals of the same species, but not the same person, or not an identical twin, between yourself and the person you're sitting next to, maybe. What he then went on to do was do a second skin graft in that same combination. And what he showed, if you did a second skin graft, you've got this almost accelerated rejection. It happened predictably a lot quicker than the first time. And what he summarised and what he was describing is that there seemed to be two responses. What's called a primary response, which was of low magnitude and took longer to develop. But when you did it a second time, the magnitude of the response or the rejection was far higher and it occurred quicker. And he's described that transplant rejection is characterised by what he terms specificity and memory. And as we've gone on to realise that this is very much a hallmark of the immune response, and indeed this is why we do immunisations. We know that if I develop the flu, having not been immunised, my response to it will be relatively small and weak and will take a while to develop. But if I'm being immunised, having had, and that will provoke a primary response, by the time I come across the influenza, my secondary response will be far more effective. But what he then wanted to know is what immune cell is responsible for this rejection response. And he did a series of experiments, what are called transfer experiments. He basically took this mouse that's had a skin graft and basically bled it and took different cells from it and then transferred them over into a mouse that had never had a transplant, a skin graft, and then did a skin graft and wanted to know when he transferred which cells, when would that result in this accelerated response. And what he was able to show is that there was something in the white cell compartment that was responsible for these rejection responses, and he was able to then nut it down further and was able to describe for the first time that it was these T cells that were responsible for the rejection responses that we see when we do skin grafts and when we do solid organ transplants. And Peter Meadoworth went on to be awarded the Nobel Prize in Medicine in 1960, and as you heard earlier, he actually co-shared it with Sir Frank McFarlane Burnett, who was one of the early directors of WEHI. So we now know that the T cell is of central importance in solid organ transplantation, and interestingly we're also going to hear about the central importance of the T cell in our next presentation as well. Now the reason it's important is that, and I'm not going to go into the details of this slide, but you can see that it's at the top of the slide. And it's very much the gatekeeper to the immune system. Once that T cell becomes activated, it talks to other cells of the immune system, which in turn talk to other cells of the immune system, such that you get an accelerated and a larger response, almost a cascading response, once that initial T cell activation has occurred. And in terms of ways of thinking about it, is that the T cell is very much the orchestra, or rather the conductor of the orchestra, and is responsible for the subsequent coordinated immune response once it becomes activated. So the question is, as a transplant physician or as a transplant immunologist, how are we going to control this rejection response following a transplant? And there's two options. And again, we use the analogy of the orchestra. If we want to switch them off, turn the music down, we can either individually knock out each one of the cells of the immune response, or alternatively, and far more successfully, you can get the same response if you knock out the gatekeeper and knock out the conductor.